Hello everyone, and thank you for the opportunity of this wonderful scholarship and learning more about hypersonic flight. My name is Jay Kumar Patel, and we're going to dive deeper into hypersonic flight going to Titan, Saturn's largest moon. Hypersonic flight refers to speeds that are greater than Mach 5, or 5 times the speed of sound. So the Mach number is calculated using dividing velocity by the speed of sound. The speed of sound is calculated using it's the square root of the adiabatic index, or the specific heat capacity based on the gases of the atmosphere, which in this case is nitrogen and methane. And the R is the specific gas constant, and T is the temperature. So using that and some calculations which I have uploaded separately, I found that Titan's reentry is approximately Mach 10, which we'll use in the future cases. So Titan's environment. Um, Titan's atmosphere is composed of 95% nitrogen and 5% methane, which makes the atmosphere 4 times more dense than Earth's atmosphere. The pressure is 1.5 bars, which is 50% higher than Earth's atmospheric pressure, and Titan is extremely cold with an average temperature of about 94K, whereas Earth's average temperature is 288. The gravity of Titan is also much weaker, with a value of 1.35 meters per second squared compared to Earth's 9.8 meters per second squared. So these create unique challenges for the hypersonic spacecraft landing. So this is the basic overview of all the challenges the hypersonic flight might face on its flight to Titan. Reaction times. At hypersonic speeds, human reaction times are significantly delayed. The average human reaction time is about 0.2 seconds. But when you factor in delays, this can extend to an additional 0.8 seconds, which adds up to 1 second of delay. At hypersonic speeds, a 1 second delay could mean a spacecraft has traveled over 600 meters in the time it takes to respond. Additionally, the turning radius at subsonic speeds is approximately 50 meters, while at hypersonic speeds it jumps to 100 kilometers. This introduces the challenge of maneuvering efficiently. To overcome these reaction time change challenges, we can integrate advanced technology solutions like AI, which could predict and react to changing conditions much faster than human operators. We could also add better sensors, which could lower delay time and help the AI make decisions faster. Cost is one of the other factors that needs to be monitored. $41 million per hypersonic boost missile guide was paid by the U.S. government. $1.4 billion was spent by the U.S. government in total for a missile. We need to find ways to make the cost lower and make it more accessible, to make it more sustainable for the long term and for space. Testing hypersonic flight is also not very straightforward. Aerospace engineers use CFD, or computational fluid dynamics, which are not very reliable at hypersonic speeds and often fail to predict real-world outcomes accurately, which makes designing hypersonic flight a real challenging. Shock tubes, which is another way aerospace engineers simulate high-speed flows, but they are very limited in scale and unable to replicate over long distance travel or at all atmospheric conditions. So this diagram wonderfully explains the design challenges of hypersonic flight. So as the vehicle travels through the atmosphere at hypersonic speeds, it generates intense shock waves, especially at the nose. The high-speed movement through the atmosphere also generates extreme heat. A hot shock layer forms really close to the vehicle's surface, where aerodynamic viscous heating occurs. And as the vehicle accelerates, the boundary layer, the thin boundary layer, transitions from laminar to turbulent flow, increasing both drag and heating. And there's also a formation of entropy layer caused by mixing hot gases near the surface, and which could impact the vehicle's stability and control. So the extreme heat and pressure in hypersonic flight put significant stress on the vehicle's surface materials. Uh, Ablation and erosion occur as like the material burns away to protect the vehicle. Also, the boundary layer is all affected by gas dissociation and ionization, where molecules break apart and ionize due to the extremely high temperatures. So these are some of the problems hypersonic flight faces, and we need to keep in mind during the design challenge. So here are the solutions to design challenges. So I created a model of a hypersonic vehicle using SolidWorks and using carbon-carbon composites on the edges, where supersonic flow, where shock waves are common and high temperatures are faced. I used titanium alloys for the body, as it's really heat resistant and could overcome a lot of pressure. The There's also ablative heat shields, which will dissipate heat and protect the vehicle. And nickel chromium alloys can be used to prevent oxidation, while the titanium nitride coatings could be used for the corrosion faced on Titan. And to further enhance the spacecraft's performance, I tried to make the edges blunt, which can help minimize heat and stress. I also took inspiration from the Wave Rider X51A, which is known for its efficient aerodynamic design. And I changed the scramjet model to be able to withstand the dense atmosphere of Titan, which would create about 15 million newtons of drag force. We would also need to have important communication technologies in the hypersonic to communicate with Earth and back. So the plasma around the hypersonic stops signal communication, and other challenges are also faced, as titanium and other alloys could interfere with signals from radio waves. Titan's own nitrogen atmosphere creates ion, which makes it even harder to communicate with Earth. And currently, estimatedly, the communication time is an hour and 20 minutes. This is my works cited page, and thank you for this wonderful opportunity.